Hello and welcome to the series of discussions on the production technology, theory and practice. So, the last topic of this subject is the engineering metrology that we would like to discuss today. Okay. Now, if you see the slides here, engineering metrology, if we have to define. So, before that, let us say that this is a machine tool carriage and this is the machine bed. Okay. Now, the carriage moves over the bed, let us say along this length of the bed to and fro. Okay. So, this is the machine tool slide way. All right. The width, depth, angles and other dimensions all must be produced and measured accurately, okay, for the machine tool to function as expected, is not it? Because it is a very lengthy machine bed and all along this the carriage has to move to and fro freely. Okay. Now, if the let us say this dimension and the dimension here, if they are not adequate, in that case the carriage may actually not move and get stuck somewhere, all right, depending on how much the deviation in the dimensions we have. Let us say if this dimension is improper with respect to this dimension, in that case also the carriage may not be able to move along the machine bed and so on. Okay. So, everything, even this angle, okay, even this has to be, this surface has to be perpendicular to this dimension has to be exactly maintained within certain tolerance level, okay, and so on. So, the width, depth, angles and all other dimensions must be produced and measured accurately for the machine tool to function. Okay. Therefore, we say that the metrology is the science of measurement. Okay. Dimensional metrology is that branch of metrology which deals with measurement of dimensions, because it is called the dimensional metrology, okay, of a part or workpiece. Let us say it can be length, it can be angles, it can be diameter and so on. Okay. Now, the dimensional measurements at the required level of accuracy are the essential link between the designer's intent and a delivered product. Okay. What is meant is that before some few lectures I discussed the concept of design for manufacturability, okay, if you remember. Now, the designer is designing a part and putting that in the form of a drawing, engineering drawing. On that drawing, the designer is actually specifying all the dimensions and what else to be done depending on the regarding the surface roughness, surface finish, okay, regarding the taperness, how fine the taperness should be, okay, cylindricity, how much the cylindricity is to be given, and all details have to be on the drawing, then only the product will be manufactured properly. So, therefore, what it is telling here is the measurement is the essential link between the designer's intent, what he wants to do, and the delivered product, because delivered product has to be exact, has to exactly match with the intention of the designer, and the intention of the designer is laid down on the drawing, okay, through the dimensions, through the tolerances, through the fits, all those things we will be discussing now. Okay. So, overall this metrology deals with the science of measurement, be it tolerance measurement, be it roundness measurement or the length measurement, angle measurement, anything, any measurement, and to maintain them is the job of the metrology, which is a science of measurement in one word. Okay. Let us see, before we go into those details, let us talk about the accuracy of measurement. We keep telling what is the precision, okay, and very often we confuse between the concept of accuracy and the precision, is not it. Now, let us see accuracy. This is the degree to which a measured value agrees with the true value of the quantity of interest. Okay. We have measured a value which actually not given, I mean not actually the true value of the quantity. A measurement procedure is accurate, okay, this is the accuracy we are talking about, when it avoids systematic errors, positive or negative deviations that are consistent from one measurement to the next. Okay. So, I will give you an example when we even make an experiment, let us say. Okay. So, let us say cutting process. You are cutting certain length and you are measuring the force. Okay. Now, with the same parameters, with the same given input, you repeat that 3 times, okay, and see what is the discrepancy each time that you are getting with respect to the other measurements, all right. And then you, this way you can actually find out the accuracy of the measurement, okay. And always in the experiments we ask that the experiment should be repeated, so that accuracy is maintained, okay. Now, once again the measurement procedure is accurate when it avoids systematic error, okay. If there is a systematic error, then of course, it is not accurate. Positive or negative deviations that are consistent from one measurement to the next, okay. Either it can be one deviation or another, but it will be consistent. Now, the precision is the degree of repeatability in the measurement process, how well it is being repeated. Good precision means that random errors in the measurement procedure are minimized, okay. Now, conventional measuring instruments and gauges are the following, that precision gauge blocks, we have the measuring instruments for linear dimensions, then we have the comparative instruments, we have the fixed gauges or the angular measurements, okay, for angular measurements. So, most of these tools, measuring tools, we will see in the laboratory when I will show you inside the laboratory. Before that I will give you a presentation also with all the tools, and we will show the tools in actual tools used in the laboratory. Okay. Precision gauge blocks, standards against which other dimensional measuring instruments and gauges are compared, okay. Usually square or rectangular blocks, you know that they are very precision, then their sizes are very accurate, all right. Surfaces are finished to be dimensionally accurate and parallel to plus minus several millionth of an inch and are polished to a mirror finish. You may remember that there are those small blocks which are absolutely smooth surface, okay. They are given with a different thickness, those are in a box, okay, and they are so smooth that if you put one on top of each top of other, it is very difficult to segregate, because their undulations are so less that they try to stick to each other, okay, and it is difficult to segregate them because they are very smooth. Usually they are normally the square or rectangular blocks. Surfaces are finished. Now, precision gauge blocks are available in certain standard sizes or in sets, the latter containing a variety of different size blocks, okay. When there is a set, as I said, that they are in a box, so various sets of those gauges are there with different thicknesses, all right. On each of these blocks it will be written what is the thickness of that, so that can be, that particular block with the written thickness on it can be used for measuring the or comparing the thickness, okay. Okay, dimensional metrology needs linear measurements, angular measurements, geometric form measurements, which include the roundness, straightness, cylindricity, flatness, etc. Okay. And the geometric relationship, that is the parallel, perpendicular, etc., concentric, runout, etc. Okay. These are the geometric relationship. and for measurement will be this flatness, cylindricity, straightness, roundness and so on. Okay. And the control surface texture, that I will come a little later. Now, the types of measurement and instruments used are the following. So, linear you all know, these are the steel rule, then we have the Vernier caliper in the linear measurement, micrometer with vernier, okay, diffraction grating, all right. So, here for example, in case of steel rule, the sensitivity is about 0.5 millimeter, okay, whereas in case of Vernier caliper it is about 25 micron. So, it is less than that, it is a more accurate than the steel rule. Micrometer with vernier, they may have the with an accurate sensitivity of up to 2.5 micron, okay, and so on. For measurement of angle, we have the bevel protractor, many of you might have seen, and I will show you in the lab also. Even right now we have some picture on the bevel of the bevel protractor, I will show you. They are also with vernier, okay. So, there are sine bars for measuring the angles. So, these are very popularly, these two, both of them, bevel protractor and the sine bar, they are very popularly used for measuring the angles, okay. Now, the comparative length, okay, for measuring the comparative length, dial indicators, electronic gauges, gauge blocks, they are used. Of course, dial indicator is not very accurate, neither it is so sensible in comparison to electronic gauges or gauge blocks. Okay. Here you can see that they are very accurate and sensitivity is very high. All right. Now, the straightness can be measured by autocollimator. This is an instrument, and this many of you might have already used it in the lab. Okay. And here the sensitivity is reasonably okay, I mean in because it is a straightness being measured. Whereas, for the transit laser beam, okay, these the sensitivity of these are even better, all right. So, these are in the micron level, for example. Now, the flatness is measured by interferometry, okay, and here are the values of the sensitivity in micron. These are where it is not written, it is micron, and otherwise it will be written millimeter per meter. Now, we are talking about the transit per meter of the length, okay, here for example. Now, the roundness is measured by the dial indicator, circular tracing, all right, and the profile can be measured by the radius or fillet gauge, dial indicator, optical comparator, okay, coordinate measuring machine and so on. Coordinate measuring machine is a very specific one. This is very expensive and very accurate. These are being, this kind of machines are being machined to used to get the points, okay, coordinates for a 3-dimensional body or the 3-dimensional figure. Okay. Now, go not go gauges, these are the plug gauge, ring gauge, snap gauge, these are the go and no go. That means, you will have the gauge, it will go or not go, I mean accordingly. So, it is a qualitative measurement, not quantitative. Microscopes, there are tool makers microscope, light section microscope, scanning electron microscope and the laser scanning. Okay. So, here also you can see that their sensitivity in microns will be different. When the laser scanning, of course, sensitivity is the high, but scanning electron microscopes, of course, they are the best in terms of the sensitivity here. Okay. Here there is a normal Vernier caliper what is shown here. So, in this, here you can see that there is a main scale, okay, and there is a vernier scale. Here there is a vernier scale as well. So, this can move along the length of the main scale, that you know, and this is the jaw. See, this jaw, between these two jaw, the internal the external diameter can be, or cylindrical jaw can be placed, and the external diameter can be measured, all right. Or the same vernier caliper can be used for measuring the internal hole. So, in that case the vernier caliper jaws, this is the fixed jaw, this is the movable jaw. This jaw, between these two jaws, the internal hole will be measured, the diameter of the internal hole can be measured. Okay. Now, here if you see that this is in given exaggerated. So, this is just to show that how to read the main scale and the vernier scale, and overall how to read the diameter when you are measuring the diameter, how to read this. That is, the main scale, whatever the main scale is showing, that is the basic, that is showing as 27. Okay. Then we will see that which line of the vernier scale is matching with the main scale. All right. So, let us say this is 42. If you see in this, that is 42 number line, 42 line is meshing with this main scale. Okay. Now, this will be the 0.42, because I will tell you why it is done, because it is multiplied, here it is written. The note that the marks on the two scales coincide at the number 42. Okay. That means 21 divisions into 0.02, this is 0.42. Each of the 50 graduations on the upper scale indicates 0.02, okay, here, and so this is given as the least count. So, this 0.02 is the least count, and whichever is matching with that, okay, this is 21, all right, that would be multiplied by the least count. So, therefore, the dimension here, what is shown here is a 27 plus 0.42, which will be 27.42. More details I will describe here now. All right. Now, how to calculate this? Let us say we will go to the same, least count is 0.02, how to find out? All right. One small division on the main scale, here you can see that this is 1 millimeter. Let us say it is specified as 1 millimeter. Okay. Now, the number of divisions in the vernier scale, you can see, let us say these are the 50, okay, number of divisions, and 50 vernier scale division therefore is equal to 49 divisions on the main scale. Okay, here if it is that, then all 50 in the vernier will be enveloping 49 on the main scale. Okay. So, each division on the vernier scale therefore will be 49 divided by 50 in millimeter. Okay. So, therefore, the difference between one main scale division and one vernier scale division, this will be 1 minus this, all right, because one small division on the main scale is 1 millimeter and on the vernier it is 49 by 50. And why 49 by 50? Once again I am telling you that the vernier scale division, 49 division on the main equal to 49 division in the main scale. If this is 50 here, that will envelop 49 of the main scale. So, therefore, it is 49 by 50, which is one division, and 1 minus that will be the vernier scale division. So, this will be equal to 0.02, and this 0.02 is considered to be the least count of the vernier caliper. So, in this way the least count has to be found out, and more and the less value of the least count, it is better, because in that case the accuracy is more, okay, accuracy of measurement. For example, here it is 0.02. So, therefore, the decimal level we can have only 2 decimal level, okay, because that is why we found out that the value is 27.42. So, you can see that there are 2 decimal level. But then if suppose if we had the least count is 0.002, in that case up to 3 decimal level we can have had the measurement. So, that means the measurement is more accurate. So, in that case of course, accordingly we will have finer scale in the vernier, that will give you the more accurate reading of the diameter. All right. Okay. Now, these are the analog and the digital micrometers. Analog micrometer has the main scale and a round scale, rotating scale. So, here it is the round one and here it is the main scale, So, this is the vernier, and then again according to the depending on the dimension that is showing here, you can read from the main scale and the round scale what is the actual reading, okay, up to the decimal level depending on the least count of the micrometer. So, this is an analog micrometer because you have to read from the scale, and this is it is the digital one, that whatever you are reading, this will be displayed on the display. That is the difference. So, a vernier, which is analog micrometer here, and the digital micrometer with a range of let us say 0 to 25 millimeter. Okay. So, within that you can actually find out the diameter. That means, you can if they are together. So, it is 0, and the maximum distance that it can cover with respect to the fixed one will be 25 millimeter. So, you can measure in this range the diameter, and of course, the resolution is 1.25 micron. Okay. It is generally easier to read dimensions on this instrument compared to the analog diameter. Of course, analog micrometer, of course, it is because displayed. So, you do not have to read. Sometimes what happens is that the vernier scale is very fine. Okay. So, to find out that which graduation is matching with the main scale is difficult. So, this has certain, this can actually give rise to certain error. So, that will not happen if it is a digital micrometer. Of course, the digital micrometers will be more expensive, but here it is easy to find out the dimension because it will be displayed. Okay. We will see the digital micrometers and the analog micrometers in the lab. Now, here that I was talking about, that this is the protractor. Suppose we have a part like this, okay, shown in the gray. This part can be placed in this, or this is rotated about this axis. Okay. So, it can be adjusted according to the angle, and then the angle will be displayed here, that what is the angle that is shown here, this angle. Okay. Yeah, this is here, it is shown in more details that there is a vernier scale and there is a main scale, and you can more accurately find out that what is the dimension depending on the depending on the least square of the vernier scale. Okay. That means, that up till which decimal level you can find out, that depends on, that is second level, that you can find out from the, that depends on the of course least count. Okay. Now, the schematic illustration of a bevel protractor here for measuring the angle, and this is the vernier. So, this is more details of the vernier scale here for angular measurement. Okay. And in this, as it is shown, it is indicating that here it is showing 14 and the minute, and in the second it is showing the 30. Okay. Now, here is a setup that actually shows the use of a sine bar. Okay. This is the sine bar in green, it is shown here for the precision measurement of the workpiece angles. So, let us say this is the part, what should be the taper angle, that can be found out from this sine bar. Let us say this is a flat and this is the tapered, okay, or both are tapered. So, in this case this taper angle has to be measured. So, in this case the sine bar is attached to this and adjusted to this surface. So, with the help of the gauge blocks, and the dial indicator will actually show you what is the angle with respect to this. Okay. Now, gauge blocks give the height, what is the height of that, and the center to center distance is known, okay, from here to here. So, in that case geometrically we can find out the angle of taper, okay, of the given block in the lab, that you normally do, and we also ask our students to do that, to find out this, because here this distance from here to here is known, and what is the height, that will be known here by these gauges. Okay. All right. Now, for measuring roundness, okay, roundness is, this is a circle, and let us say the part is this. So, in this case I can see that part is not really circle. Of course, this is highly exaggerated. All right. It does not happen so much, but when you highly exaggerate, let us say this is visible like that. So, this can be measured by the dial indicator while putting the cylindrical job on a V block. Okay. This is the V block and this is the cylindrical job which rotates, okay, that is rotated manually of course, or putting that on the centers, for example, as it is shown here. So, these are the centers, it is rotated about this about these centers, and then dial indicator shows you that what is the out of roundness, let us say in this cross section. Then it can be put it in this here, in this cross section, in this cross section, and so on, and the average can be taken along the length, all right, along the length. So, or it can be put it on a V block, as I said, it can be rotated manually, and then there is a dial indicator in, and here there is a stylus of the dial indicator. So, this is inbuilt, let us say, and the dial indicator will show what will be the out of roundness. So, this is the schematic illustration of out of roundness. Okay. Now, this is the measuring roundness using the V block and the dial indicator, okay, part supported on centers and rotated, and here if you see that this is a circular tracing. Now, the part is here in the green, all right, and here these are the clamps which help in clamping the part on a base. Okay. This is the rotating precision table, it rotates, and this is the probe. Okay. So, the probe is a stylus, and that stylus is equivalent, like the stylus of the dial indicator. So, this is the dial indicator and with the probe, and depending on the out of roundness of this, when it is rotating, it will actually show what will be the out of roundness. Okay. So, circular tracing with part being rotated on a vertical axis, here it is on the vertical axis, it is rotating, all right. Okay. And here if you see that here and here they are with respect to the horizontal axis, the part is rotating about the horizontal axis. Now, the mechanical gauges, dial indicators are designed to mechanically magnify the deviation to permit observation. Okay. Most common instrument in this category is the dial indicator, which converts and amplifies the linear movement of a contact pointer into rotation of a dial. We will show you, I will show you later that what does it mean, that converting and amplifying the linear movement of a contact pointer into the rotation of a dial. Okay. The dial is graduated in small units such as 0.01 millimeter, okay, or even it can be 0.001 millimeter and so on, depending on the accuracy of the dial indicator that I already told you. Applications are for measuring straightness, flatness, parallelism, squareness, roundness, and runout. So, these are the purposes for which the dial indicator can be used. Okay. Here is the dial indicator, this is the probe, and this probe is connected to the gear train, and those gear trains are extremely sensitive. Okay. So, therefore, as the probe goes up and down depending on the undulations, okay, in that case this will be highly magnified by the gear train which is here, and then accordingly the indicator will show you the deviation, or the indicator will show you what will be the what are the discrepancies. So, for example, if it is suppose if it is the undulations you want to find out on the surface, okay, surface roughness, let us say this is the surface highly exaggerated. So, when the dial indicator will move on this, the dial indicator will go up when it will come here. If it is, let us say this is the mean line on which the dial indicator will go, dial indicator pointer is here which is 0, then when the dial indicator is moving it will come at this point here. So, then the dial indicator will go up, then again it will go down and so on, and this will be indicated by the pointer here. Okay. Now, accordingly you will find out what will be the roughness values, and similarly we can also find out what is the value of the out of roundness, all right, because we said that for straightness we can find out, for the flatness we find out, parallelism, squareness, roundness, okay, runout, all these defects, okay, we can actually measure using the dial indicators. Okay. And this is the design of the dial indicator. Now, roundness and cylindricity, let us give you a basic concept or the definition of the roundness or circularity, all right, is the two dimensional tolerance that controls how closely a cross section of a cylinder, sphere or cone is to a mathematically perfect circle. Okay. So, roundness is a circle, mathematically perfect circle is round, where on the periphery all points will have a same radius, all right, from the center. Now, here we are saying the circularity or roundness is the two dimensional tolerance, okay, that controls, that says how closely a cross section of a cylinder, let us say if this is a cylindrical part. So, then at any point here we have to see that how much it is deviating from the perfect mathematically given circle, that is what the roundness is. Okay. Now, consider a cylinder whose purpose is to roll along a flat surface. Okay. A small flat on the outer diameter of the cylinder would detract from how smoothly the shaft can roll. The flat spot can even be so large that the shaft cannot roll at all. In this case, the flat represents a deviation from a perfect circle that can be measured quite accurately. So, this is just an example, we are exaggerating by saying a flat. So, what we mean to say is that it is the cylinder whose purpose, when it is rolling along a flat surface, and if there is a flat on the cylinder, it cannot roll. Okay. So, it is out of cylindricity by saying that there is a flat on a shaft, meaning it is out of cylindricity. Okay. Now, cylindricity is the out of roundness. The cylindricity is the three dimensional version of a roundness. Okay. It assesses how closely an object comes to a perfect cylinder, meaning that it is not only round, but also straight along its axis. The simplest example that demonstrates the need for cylindricity is a pin. Okay. This is required to pass completely through a bore with a tight dimensional tolerance, is not it? Now, if the pin is bent, it may not pass through the bore. So, that is what we are saying, that then it is not the cylindricity. Coaxiality is the tolerance for how closely the axis of one cylinder is to another one. So, whether they are coaxial or not. Okay. Now, example of coaxiality is a shaft having two diameters. Okay. So, I showed it to you, right. So, this is a shaft and this is a shaft, and it may be the same axis, diameter D1 and diameter D2, both have the same axis, all right. Perhaps two bores located on opposite sides of a housing, all right, they also have the same axis. In either case, the center of one element is expected to be along the same axis as the second element, is not it. Now, since each element is being assessed as an axis, coaxiality is the three dimensional measurement, therefore, we are saying. A special case of coaxiality is the concentricity. Okay. Now, here when concentricity occurs, when a part is measured at the same cross sectional plane, making it a two dimensional measurement. Okay. Now, the most common example is comparing the internal diameter and the outer diameter related to each other on a hollow shaft or a tube. When the tube is hollow, in that case when you are considering the internal diameter or external diameter, here the concentricity will come into picture. Runout is a two dimensional measurement, okay, that can be either be taken in the axial direction or in the radial direction. Now, here of course, this is the explanation given. Runout takes into account both the axis offset and the roundness of any object that rotates about an axis. This is important. All right. Now, here when measuring the radial direction, Runout combines both roundness and concentricity errors. Okay. This is also important here. Okay. Now, this is more or less the already explained. All right. Now, here these are the diagrams where through which we are actually showing that what is the circularity, actual surface, maximum radius, minimum radius, and how this can be designated. So, the tolerance of circularity on a drawing can be given in this way. This we are actually coming in more details in a table. This is the tolerance for the cylindricity on a drawing. So, all these symbols are actually tabulated. Okay. This is the cylindricity definition. That means, here we have the smallest cylinder, this is the largest cylinder, and within that it can fluctuate like this from point to point. Okay. And this is how it is given, it cannot be more than 0.05. So, 0.05 is the tolerance zone here. Okay. And here it is 0.06. So, 0.06 is shown here. Okay. These are the definition of the straightness, okay, and the tolerance for straightness on a drawing can be given in this way, that when you have the surface. So, you are showing it in this way, that this is the straightness which is within 0.05, it cannot be more than 0.05, it should lie within this value. So, this is called the tolerance zone. Now, flatness, okay. Here we have the imaginary planes, okay. This is the actual profile, but absolutely flat profile if we are putting it with the lower line, okay, with the peak valley and the peaks, all these peaks and the valleys. So, this constitute these two lines. Difference between these two lines or these two planes, imaginary planes, is the tolerance zone. So, this is how the flatness on a drawing can be shown. So, this is the drawing, let us say this is a surface, and the flatness of this surface should not be more than 0.08 millimeter. Okay. When nothing is mentioned here in engineering drawing, it means that this is in millimeter always, by the way. Okay. Now, next that we see is the profile measurement. So, profile measurement is important, particularly the lab when we measure the gear profile, for example. Okay, it can be the bevel gear, it can be the spar gear, okay, it can be the worm and worm gear. So, this is important to exactly find out what is the profile. So, here you can see that here a gear tooth is shown here, okay, and this is how the gear tooth thickness can be measured with the help of a caliper, Vernier caliper, all right. And here is the micrometer, ball and micrometer, because ball is made so that ball is used so that it sits on the pitch circle diameter of the gear. Okay. So, this will be accurately measuring the thickness, okay, tooth thickness and the profile. Let us say introduction to tolerance. What is tolerance? All right. We have a part, and this part, this is the pictorial view of the part, but this is the drawing. All right. Now, in this drawing there are three views shown and all the dimensions are visible. These are given according to the designer's intent, all right, and a designer is telling that it has to be, this hole has to be of this diameter, for example 1, and this has to be 1.5 and so on. Now, when the manufacturer makes this part, the manufacturer may not be able to maintain exactly that size, all right. So, therefore, it is not possible to maintain exactly 1.5 unit of something, let us say 35 millimeter of a length or 25 millimeter of a diameter. It is very difficult to maintain that length exactly. So, therefore, there should be some kind of variation in that length that is accepted by the designer, and accepted by the designer means that if it is 35.01 millimeter, it is okay, still the assembly can be done, or if it is 34.995, still it is okay because it can be assembled. I am giving you an example only. Similarly, on the roundness also or sorry, on the diameter also, you can have some kind of a tolerance, because the exact diameter is very difficult to machine. Okay. So, this is the concept of tolerance. Can more than one or multiple parts be produced with exactly the same dimension? So, we said that it cannot be. Now, the allowable deviation from a standard, for example, the range of variation permitted in maintaining a specified dimension in a machine piece is the tolerance. So, this is simply taken from the Webster dictionary, how the tolerance is defined. So, this is the allowable deviation. Allowable deviation, I gave you example. This means that if we have this shaft can have the maximum diameter this, okay, and it can have the minimum diameter like this. So, the tolerance will be this much from here to here. This is the concept of the tolerance. Now, therefore, a tolerance is the total amount by which a specific dimension is permitted to vary. The tolerance is the difference between the maximum and the minimum limits. Okay. Variations occur in any manufacturing process which are manifested as variation in the part size. Tolerances are used to define the limits of the allowed variation, how much we can allow. That is why it is called the tolerance, how much you can tolerate. Okay. So, this is the American Society's definition of the tolerance. Okay. Why it is necessary? Because it is impossible to manufacture a part or a component as an exact size or geometry and so on. Okay. Now, since the variation from the drawing is inevitable, okay, acceptable degrees of variation must be applied. Large variation may affect the functionality of the part, because suppose if it is to be assembled, let us say that shaft that I gave you an example, that shaft goes into the let us say inner bore of the bearing. Okay. Now, if it is not within the tolerance, then the shaft may rotate with respect to the bearing, that we do not want. Suppose we want the shaft to be rotated along with the inner races, okay, of the bearing. So, therefore, if it is very if the diameter is bigger than what is within the tolerance zone, then it cannot be assembled. That is another problem. So, what I mean is that the large variation may affect the functionality of the part. Small variations may affect the economy of the part. Okay. This you understand what is said. Cost generally increases with the smaller tolerances, because if it is very tight tolerance, let us say 0.0001. Okay. So, you cannot really get it within that fine tolerance, and if you have to get it, then the machine has to be very accurate. So, then the cost of the product will be very high. Parts with smaller tolerance also is called the tight tolerance, okay, often require special methods of manufacture. Parts with smaller tolerance often require greater inspection and call for rejection of the parts. Okay. Now, it can be dimensional or geometrical. Okay. The total amount by which a specified dimension is permitted to vary. Let us see here. This is the here we have the hole. Okay. This is the hole, and here is the shaft. Okay. So, for the shaft, this is the minimum diameter and this is the maximum diameter. So, this is the tolerance. Okay. For the hole, okay, hole is the basic size of the hole is this, all right, from here to here. So, this line we are calling as a zero line or line of zero deviation, all right. So, therefore, from this zero line, how much we can have as the deviation. Let us say we are saying that we can have up to this. Now, it is exaggerated, of course, you understand that. So, we are saying that the whole diameter can be from here to here. So, this will be the upper deviation. Okay. In case of shaft, this will be the upper deviation from here, right, because upper deviation for this will be from here and this is the lower deviation. So, that means the shaft cannot, this means that the shaft cannot have more than that, this is the upper deviation, and the shaft cannot have less than that, that is in the deviation. Okay. The basic size, basic size I already said to you, told you that this is that. Now, the minimum diameter is here and let us say the maximum diameter is here. Okay. So, the tolerance will be from here to this, tolerance will be from here to this, and here the tolerance for this will be, this is for the shaft and this will be from here to here, this is the tolerance from here to here, this will be for the hole. Okay. Now, in here of course, we will show you in more details little later, let us say in the next diagrams. Limit of size, maximum limit of size, minimum limit of size, shaft and hole. So, these are the definitions, some definitions, that is limit of size is the two extreme permissible sizes of a part between which the actual size lie. All right. So, maximum limit, therefore, minimum limit, these are variation of the limit of size. Shaft and hole terms, these are used by convention to designate all external features of a part, including those which are not cylindrical, okay. And internal, when they are mentioned, this is through the hole term. Now, here you can see that what is allowance and what is tolerance. So, allowance and the tolerance is given in this diagram. Let us say this shaft goes into the hole, all right. So, these two lines coincide. In that case, we have a tolerance in the shaft as this much and tolerance in the hole as this much, meaning the maximum diameter of the hole can be this and the minimum diameter of the hole can be this, so that this shaft can goes in here. These are all very exaggerated, you do not misunderstand that this will never be fitting well there, all right. These are just to show, these are very highly exaggerated. So, accordingly you will see that the allowance that we are giving is from this, is the definition, as per definition it is from here to this line, okay. That is the lower of the hole and the upper of the shaft, upper limit of the shaft, okay. This is what it is still told here. Tolerance zone, upper deviation, lower deviation, that I have already shown you in this diagram, all right. Now, here also it is shown the same way that I have already shown it to you, those definitions, that the tolerance zone for hole will be here, it is given in a better way. So, you can see this. Now, here we are saying that this is the 0 line. From with respect to 0 line, we will show the upper deviation, lower deviation and the tolerance here, okay, with the basic size of the shaft and the hole. So, with the minimum size of the hole here and the maximum size of the hole here. Similarly, for the shaft also it is shown here, you can see this. Now, see, the main thing what we are telling is that, well, I will show it to you in a drawing. Let us say for example, we have a shaft, okay, and this shaft has a chamfer and it goes in a hole here. So, our basic concept is the following, that once it goes into the hole, let us say this is the shaft, okay, and they are coaxially made. So, if this, suppose we want this shaft to be snugly fitting inside the hole, snugly fitting means tightly fitting, all right. In that case, this diameter of the hole, internal diameter of the hole should be should not be more than the outer diameter of the shaft, that is one thing. Now, how much it should not be, how much more, that means the shaft diameter should be little more than the internal diameter of the shaft, internal diameter of the hole, so that it can actually go very tightly, sit very tightly. That is the concept of this. There is a tolerance has to be given accordingly. I will show you what are those groups of tolerances depending on which it is given that two mating surfaces are tightly fit with each other, or it is not so tightly fitting with each other. Let us say these are given in the unilateral tolerance in one side, okay, or it is on the bilateral. So, these are from both sides tolerance will be given, okay. It is like that. This is the bilateral, so both, or unilateral, one side will be 0, okay, and here both sides will be toleranced. That means upper limit or lower limit both will have some limit. Here the lower limit is 0, upper limit is this. So, this is called the unilateral therefore, and this is called the bilateral. So, this is exactly what is shown here, but it is through the tolerance zone. Okay. All right. Then we talk about the fit. A fit may be defined as the degree of tightness. I just started telling you about the shaft going into the hole. Okay. So, when we are having an assembly drawing where parts are shown with respect to each other, then we have to give the fit and tolerance to be given on each part. Okay. How the part dimension can be deviated from the actual diameter or the length, that is called the tolerance, and the fit is when it is in the assembly how they are fitting with each other. Okay. So, fits can be clearance fit, transition fit, or the interference fit. Clearance fit where the hole minus shaft. So, clearance fit is that the shaft diameter is little less than the hole diameter. This is basic thing. Okay. So, this is the loose joint. All right. Now, the clearance is the hole minus shaft, okay, hole minus shaft, and the hole is bigger. All right. So, this is more than 0, hole minus shaft. Now, the types of clearance fit can be loose fit, running fit, slide fit, or medium fit. So, these are depending on the level of fitness. Okay. Similarly, we have the interference fit when we will have the hole minus shaft is less than that. That means, we have the hole diameter is less than the shaft diameter. So, this is the interference fit. All right. Diameter of the shaft is always larger than the hole diameter. So, it snugly fits, tightly fitting. Okay. Now, the types of interference fit also are different. Shrink fit or heavy force fit, heavy force is required. So, the diameter of the shaft is much more. Medium force fit, medium, and the tight fit or force fit. So, these are the different kind of fits are there. Those are all interference fit. Transition fit is, it is neither very tight nor very loose. Okay. They are a compromise between the clearance and the interference fit. Okay. They are used for applications where accurate location is important. All right. Location has to be very accurate, but either a small amount of clearance or interference is permissible. That is what it is telling. Now, the types of transition fit can be push fit or snug fit, force fit or shrink fit, okay, or ringing fit. So, these are the various types, but all of them are transition fit depending on how much is the level of the transition that in each of them. Okay. So, here it is defined, and that is defined based on the level of the transition in the fit. Okay. Here you can, this is very important thing that we can use the dimension which is hole basis or the shaft basis. So, normally we use the hole basis, and why it is that it is shown here clearly. Now, use hole basis system so that the minimum tolerance on the hole is 0. Here you can see that this is the hole basis system. Okay. So, minimum tolerance, this hole is 0, okay, and depending on that we have the tolerance of the shaft. You can see that these are the different kind of tolerances. Depending on that, if you have the tolerance zone somewhere here, it will be clearance fit, because then the shaft will be loosely fitting on the in the hole, and if the tolerance level is here, so this will be the interference fit, because very tight, and these are the transition fits in between. All right. Now, similarly, if it is a shaft based system, then we will have the minimum tolerance zone is this here of the hole, and the tolerance zone for shaft will be here with the 0 line, and since here this was the hole base, and for the hole base 0 line is coinciding here, then for the shaft base 0 line will be coinciding and shaft will be on this. Okay. This is the tolerance level. Now, hole then is changed, but why we said that you use the the hole basis, because the tolerance on hole is minimum tolerance is 0. Okay. Here you can see that minimum tolerance is non-zero for the hole, which is very difficult to make, in the sense that when you have made a hole, okay, you have a particular minimum tolerance. All right. See, you can increase the diameter of the hole, but you cannot decrease it. But in case of shaft, you have the diameter that you can actually decrease, but you cannot increase, right. So, therefore, the whole system should be used normally, because the minimum tolerance on the hole is 0 here, this system that is showing here. Okay. Types of fit is given here. So, this is the hole based system, and the hole is constant, and then the shaft is changing. Okay. Shaft diameter is changing. So, depending on that, we have the clearance fit or the transition fit or the interference fit. Okay. Now, the of course, we said that the clearance fit, this is when we have the clearance between them, but that means the hole and shaft are loose. So, I mean relatively loose, let us say, and schematic representation of the transition fit, that is in between the very tight and the loose, we will have the transition fit. Okay. So, this is all in the hole basis, because once again I would like to repeat that in the hole basis the whole diameter is fixed, and then depending on that you adjust the shaft diameter, that is the idea. Okay. Here is the system, this is given in more details. So, these are the internal holes, okay, and this is the shaft external feature. So, here you can see that H is the lower value of tolerance, okay, and H here is this is the shaft system. So, normally we say that we use the whole system, okay, internal features, and lower value of the tolerance is given. So, A, B, C, D, all the alphabets are used, and this is the difference between them here in this diagram. You can clearly see this. So, depending on that, you can have the fit and the tolerance given on the part given tolerance, and fit can be given in the assembly drawing or the sub assembly drawing. So, here depending on the clearance between them, okay, you can define with this kind of whether it is a clearance fit, whether it is a transition fit, or whether it is a interference. That is all I wanted to tell you about the fits and tolerances, and overall about the on the course, in the course of this that we have discussed with the 5 modules. All the 5 modules together, they actually constitute the core. The course along with the lab parts will show you the lab in the lab different kind of processes, including the NC and the CNC machines. So, this is the production technology, science, theory and practice. Thank you for your attention.